Writing a detailed system prompt provides instructions to a model, but that alone does not create an autonomous agent. For years, the industry focused on tuning model weights. Then, attention shifted to context engineering, optimizing the exact text a model sees in a single generation call. But a true autonomous agent requires a new architectural layer, the harness. This software wrapper manages state, routes logic, and executes tools. Harness engineering focuses on customizing the substrate, treating configuration as a first-class component of the system architecture. Modern coding tools like Cursor, GitHub Copilot, and Claude Code expose this harness directly to developers through versioned repository-level artifacts. These tools offer a fully configurable, autonomous architecture. The question is whether developers are actually building within that architecture, or if they are primarily committing basic Markdown files to their repositories. To measure the actual capability of agentic tools today, we have to look past the context window and analyze how this entire software wrapper is built in the wild. The design space for this harness consists of 8 distinct configuration mechanisms. We can organize these mechanisms along a capability axis, moving from static instructions on the left to fully external connections on the right. On the static end, we have context files, rules, and settings. These mechanisms strictly inform the model. They do not execute code. This is where you find standard artifacts like a CLAUDE.md file or a project README specifically tailored to establish an agent's coding conventions. The middle zone is where the harness takes autonomous action. This executable layer comprises skills, subagents, commands, and hooks. Subagents act as parallel loops running in their own context to handle multi-step operations. Hooks operate as event callbacks triggered dynamically during the agent's workflow. Finally, on the external end, MCP servers connect the harness directly to outside APIs and external systems. The static end is cheap to author and carries low risk. The executable and external mechanisms require more trust and introduce a wider security surface area, but they offer significantly more power. Static files are an easy starting point. However, the capacity to automate complex software engineering tasks requires moving into the executable and external zones. Knowing these 8 mechanisms exist is different from knowing how they are used. We need to see what developers actually commit to their repositories. An empirical study recently set out to measure this, starting with a dataset of 37,249 actively maintained GitHub repositories. Researchers filtered that volume down to strictly engineered software projects with English READMEs. That left 2,853 repositories containing detectable configuration files. By cloning the default branch of each repository, the research team could scan the artifacts inside and categorize them into the 8-part taxonomy. The detection relied on specific directory and file name heuristics. This is a noisy method. A misnamed file will simply be missed by the scanner. The sample is public, open source, and English-centric. It tells us nothing about how proprietary enterprise teams configure their agents behind firewalls. Most importantly, this data strictly measures adoption. It counts which mechanisms are present in a repository, not whether those configurations actually produce a better agent. Even with the heuristic noise and sample bias, this pipeline establishes the first reproducible empirical baseline for how AI harnesses are configured in practice. When you look at the exact counts across those 2,853 repositories, a very specific pattern emerges. The static category absolutely dominates. Context files were detected in 2,586 of the analyzed projects. For most of these repositories, a static Markdown file is the only harness mechanism. The adoption gap for advanced features is massive. Out of 3,000 projects, researchers found skills in 158, subagents in 131, MCP integrations in 75, and hooks in just 42. Even when developers use the skills mechanism, which sits in the executable layer, they primarily populate it with static text instructions rather than functional code scripts. There are some variations based on the tools developers choose. Claude Code users, for example, employ the broadest range of configuration mechanisms across the taxonomy. Agentic tools offer deep autonomous capabilities, but harness engineering in the real world is bottlenecked. The configuration practice remains overwhelmingly static. This baseline provides clear directions for software teams deciding how to architect their repositories today. First, AGENTS.md is quickly becoming an interoperable standard across multiple agentic tools. Adopting a static context file is the baseline requirement. It is a low-friction starting block for any codebase utilizing AI assistance. The executable and external mechanisms on the right side of the axis represent a latent opportunity that most developers have yet to touch. The current adoption cap exists for a reason. Writing executable agent scripts and opening external connections carries higher authoring friction, requires more testing, and expands a project's security surface area. Relying on a single prompt ignores the architecture required to manage state, execute code, and maintain context over time. The next stage of development will likely center on these underused executable mechanisms, probing whether engineering the full harness can bridge the gap between static instructions and truly autonomous action.